So, the last slide of the last lecture was giving you in lasers, use of lasers in medicine, and there I spoke about the LASIK technique, which has become very popular and very successful too, and also the fine cut given by lasers to make coronary stents. So, but then the use of lasers in medicine is much more than just a scalpel. Okay. So, it has been used in lasers for treatment of cancer. Mainly here I just give you an example of the tumor removal with different wavelengths of beam, different wavelengths depending on the tissue that you are trying to ablate. So, it can be done this way: you use the laser power to ablate that complete tumor itself, or you do it in stages to cure the body of tumor. Cure in the sense removing it out of your body. So, and different power levels are used depending on the extent of the tumor, the spread of the tumor, and the type of the tumor. So, all that will give you which wavelength of the beam to use and how much power levels to be used. So, lasers are widely used in this kind of a treatment, and many other cancerous treatment are also under the research wing, which hasn't come out into the market completely, but a lot of research is being done to manage cancer with lasers. Okay. And another important one compared with the eye, in continuation with the eye operation, is the retinal detachment. How to cure retinal detachment? In fact, you have to attach the retina back. The retina gets detached from the tissues in which it is on which it is lying, and you have to attach it back. So, basically what you are doing with the laser is you are welding those small parts, welding those actual live tissues back onto the base tissue of the eye. So, as you know, the retina comes at the end of the eyeball, and the front part is of course the lens. So, the lens only acts as the lens of the eye acts as a focusing device, which will focus, say, something like a red laser, yellow laser, or green wavelength lasers. These are the ones which are generally used, partly because the lens is transparent to these wavelengths, and then the lens acts as a focusing device to focus on the part which is detached and has to be welded back onto the other tissue. And another pulsed ruby laser has also been used, around 300 microseconds, that means pulsed duration, and energy below 1 joule is good enough for this kind of an operation. And these colors of the laser are also chosen depending on the pigment that is there on the retina, or in some part of the eye. Okay. So, the choice of your laser wavelength will also depend on that. So, this is where I stop talking about lasers in medicine, but there are numerous uses of lasers in medicines. Those who are interested can just read up some more. I have given you the more prominent ones and the more successful techniques with lasers that have been used. Okay. So, next I go on to another subject in the sense in case of uses of lasers itself, but here we will be using the property of lasers, that is low divergence. So, I will be using this property. Okay. Property of the laser used is a very low divergence of lasers. You already know that lasers, you get an output which is a pencil thin line. Okay. And what is that technique? The technique is called LIDAR. You definitely must have heard about LIDAR. It is a very, again it is a very successful technique. Okay. And it stands for light detection and ranging. Okay. So, it comes from the, it is a sort of kind of another case of radar, which is radio wave detection and ranging. So, in place of radio waves you have light waves. But the same thing, you know, the same principles are used. You want to range the object, you want to know how far is the object, you want to know what does the object that you want to study, how much absorption it has, how much emission it has in the wavelength that you are using. You want to know everything about that object you are trying to range. Okay. Okay. So, in its basic form, absolute basic form is given in this yellow square box. Okay. So, in its basic forms you have a light form which is a transmitter or a source of light. Okay. I have not said whether this is a laser or not, it can be any light, okay, any light. The principle is you let that light go to your reflector, you keep a reflector here, and some part of it gets reflected back, and you put a receiver here or a detector here which will detect that light. So, the light has gone from here to here and then this has detected, okay. And this part is called the time of flight. The time this light takes to travel from here to here and back to the detector, exactly where your light source is sitting. Okay. So, that is the transmitter and this is the receiver. So, this is the very basic idea of a LIDAR. Now, if I were to expand it a little bit more, it would look something like this. Okay. Okay, before I come to this part, let me just explain that low divergence part. Okay. If you remember, this diagram you would have seen when we spoke about resonators, you know, and the kind of beam that is produced in a laser resonator, where the divergence, when I say low divergence of the beam, I must know what is theta, which gives the divergence. So, this green part is the laser beam which is diverging out from the minimum spot which is given by W0 or omega 0, whatever you want to call it. Okay. So, this is the smallest spot size, but then it has diverged and gone out, and at some point along the z axis, because the beam is travelling along the z axis, you want to know how the spot size has changed. Okay, and that is W. Okay. So, this is what I had described before to you when we were speaking about resonators. So, just recollect all those formula that we had put up, which is given here. I have repeated once again here. So, what I want is, I want theta, which will give me an idea of the divergence of the beam that is coming out of the laser oscillator or the laser system. So, theta is given by lambda W0 pi. That means it depends, the theta, the angle of divergence, depends upon the wavelength that is being used. It depends upon the smallest spot size. So, the smallest spot size is at the laser itself, just at the output of the laser. Suppose we take it, in this case that is the case. So, this is my laser and I want the spot size at this point, and then this is the z axis. So, this is W0, what I start with. Okay. So, W0 is the spot size at this point of the laser, okay, and then it diverges out, and I am trying to find. So, this can be experimentally seen, W0 can be experimentally seen, and lambda means you know the wavelength that you are going to use for your LIDAR, and once you know that, you know theta. Okay. And from these formula you can find out the spot sizes at different points. This also gives you the likely spot size at the smallest point of the beam. Okay. This is inside the resonator, but here I want some spot size which is outside the resonator. Okay. So, this also helps in finding out the spot size at this point. And this is Wz, which is this W or omega, W, I will call it W. So, that is the spot size at this point of Z. So, I have all the characteristics of the beam. Now, your theta has to be very, very small. Okay. You want the theta to be very small so that the divergence is low, and that is a characteristic of most lasers, but you need to make an estimate of that before you design your LIDAR, because you have to find out how far this beam has to go up to the object and then return back. Okay. One more thing I should mention here is R is the radius of curvature of this phase front. Okay. So, you need that also. Okay, and theta is the divergence angle. Generally in LIDARs, this theta is around 0.1 to 1 milliradians. Okay. So, it is given in milliradians because it is so small, it is so tiny, but in degrees, radians is equal to 1 in degrees 180 by pi. Okay. Okay, so, you just have this conversion from radians into degrees, you can just multiply or divide by 180 by pi. So, you get that conversion part. So, a 0.1 milliradian is very tiny. Okay. Now I will go to the slightly detailed part of this yellow rectangular piece, which is here. By the way, because we are measuring, we are depending on the measurement of time of flight, we have to take a pulsed laser. Okay. A continuous wave will not give you any idea of the distance. Okay. And distance is the main thing, because we call it light detection and ranging. What is the range to which of the object from the laser? Okay. So, suppose I start with a square pulse like this, and it has to travel this distance d. It can be here, it could be like this, and then it reflects back from there, and with a photodiode you can check out on the what kind of a pulse returns back. You see it on your oscilloscope, and your pulse may look something like this. This is only representative to say that it may not look exactly like the input pulse, okay, because it would have lost some energy or power on the way back and at the scattering point. Here I called it a reflector, but a reflector is just a name for the object that you are trying to pinpoint and measure. Okay. So, it can it would have scattered a lot of the light. So, you do not get back the exact pulse, and so you get a different shape also, but what you are not interested in all that. If you just want the distance, then all you need to do is measure the time. This t, small t, is the time of flight. That means this total time going there and coming back. Okay. And this one here is the reference. The moment you send that beam, you have that reference with you, and the moment the pulse comes back, you have that case. Okay. So, this is the range detector, you might call it something like that, and this is the intensity. Okay. So, that is how you are doing it, pretty simple enough, but in actual practice, when you use the LIDARs, they can become very, very complicated. Okay. But as a concept, it is not very difficult to understand. Right. So, here is what, and you understood we need a very low divergence to the beam. Okay. And most of the time these LIDARs are used for remote sensing. Remote sensing, because you want to sense what is remote from your instruments. Okay. So, so remote sensing is another way of referring to LIDARs. Okay. So what are the things that they do? So in remote sensing, you have the emission of the laser pulse, which we have seen there. Rapid pulses are sent out, okay, and then you have the reflection of light, okay, reflection of the laser light. The laser pulses hit objects on the ground or environment and reflects back to the sensor. Time of flight calculations measures the time for the light pulses to return. Using the speed of light, the distance of the object is calculated. Okay. And then you have to analyze the data collection, combining distance data, initial data, GPS to get a 3D representation of the target. So in short, I have just put down there what are the whatever I explained in the previous slide. So now that data collection is a very important part of the LIDAR itself. See, if you you have to basically analyze the data. That means you have to know till what distance did my laser travel and travel back. Suppose I talk about measuring aerosols in the atmosphere. So here I am sitting on the ground. I have this laser which has gone up to the aerosols and reflected back. Okay. So how do I'll describe what aerosols are. Actually just small particles, very, very tiny particles which comes in a spray. You know, if you can spray, it could be mist, it could be small spherical balls of liquid and particles, and it could be the atmospheric pollution particles, very tiny particles. You know, it has some size limitation is there till when you call it an aerosol and when you call something else. Okay. So, so here is the laser which is going up. Now suppose your atmosphere is absolutely clear. Okay. So this laser has gone up and it has come back, reflected off some molecules, air molecules, nitrogen molecules, oxygen molecules. It has reflected off that and it has come back. Once it has come back, what you have to do is you plot a graph. This is the range or the height from the time of flight you have calculated, time of flight it takes. You know what is the range of that particle in the atmosphere. And then this is the backscattering of the laser radiation. Okay, the laser radiation which has backscattered. So basically this is the graph which has which your sensor has detected after the whole time of flight. Okay. Now you get a nice little smooth curve, because the atmosphere was clear. Okay, and some of its intensity has reduced because of the scattering with nitrogen molecules and oxygen molecules and such. Okay, not they are very tiny particles, so you are getting a very smooth pulse. But suppose you have aerosols there which have a slightly bigger size than the nitrogen or the oxygen. What comes back would be a pulse like this. Okay. So the beam that has come back, it has hit some particle which is different from the molecules, and you know, the intensity has got kinks like this. And if you do the ranging for that, that means you find the height, you find the distance the laser has traveled at this point and at this point. Okay, there are two, some particles are here and some particles are at this height. So you've converted your time of flight into your height. Height because height you are taking from the ground where your instruments are, and you are sending it up to the aerosol, to the atmosphere and back. Okay. So you get a height. So you know the pulse that is coming back is not, it's not just the time between the emission pulse and the detected pulse. It's not just that, there is more to it. If you see the way the pulse has changed its shape, that also gives you a lot of information. So it gives you that information about the height of the aerosols. You do have aerosols at this height, you have aerosols even at that height. So it has given you more than that, and it has also told you that there are aerosols there. It's not just the nitrogen and say oxygen molecules, okay, of the air. So it's given you a lot of information, and the different kinds of information you can get much more than this is by just changing your detector at the receiver end. At the receiver end you can put a spectrometer, then perhaps you will get some spectral lines which characterize the particles of the aerosols. Okay. So basically your detector can be anything that you wish to measure. Okay. Now suppose I have a drone or an aeroplane where I have put my LIDAR, I have put my laser there, and it is coming down towards the earth. Okay. So here it's coming down towards the earth, it's measuring the terrain, and then from the ground it reflects back something. From the trees, here I have just shown a tree, it reflects back something. From this part of the tree it reflects back something, and all of them are recorded, all those pulses are recorded. I have given, and the emission is say like a pulse like this, just for the sake of understanding. It's a pulse like this. It need not be an exact square pulse. It can be anything, because you are only interested in the time of flight. You are not interested in anything else. Okay. So it can be any sort of flight. So when it goes to the ground, it has it between this point and this point, that's the maximum time. Okay, maximum time taken. Okay, because you're from the ground. So this time of flight gives you an idea of the distance of the ground from this point. Then this part gives you this part of the tree. You know, the tree, this portion of the tree has reflected back something, and that gives you another pulse. And the pulse, if you see, has widened compared to this, and it has reduced in power or intensity here, which is understandable. Okay. So so you get, okay, this was on the ground, this was this part of the thing, and you can get one more pulse which is from the ground. So the ground is the maximum distance, this is the next one, and this is the next one. So you can get 3 or 4 pulses like that, and you measure the time and you know the distance. Okay. So this is generally used a lot in mapping the terrain. Okay. So when I show this beam, it is actually a beam with a very low divergence, and you can scan it. You can scan it from here to here to here. Each time you scan, you are getting a different time value, and you are converting it into the height. This is the altitude that I have put here. The time goes this way, and conversion into altitude goes this way. Okay. So you can sort of map the terrain, and you can pinpoint exactly where that terrain is, because you've connected up your data collection system to the GPS. Okay. And you can do a 3D mapping. So the laser sitting on a plane is scanning the whole land below. Okay. Is scanning everything there. Once it has scanned everything, you have to analyze the data, and that data is connected to the GPS. So you get that exact position of that terrain, and you get what that terrain looks like. Does it have a mountain? Does it have a river? Does it have a jungle, and such? Okay. And such things, this has become very popular in archaeology. Archaeology, because you can map the terrain. suppose you choose your wavelength such that the laser can penetrate this, penetrate the leaves and the vegetation and all that, and goes below, and it reflects back from the rocks or whatever, whatever stone building or something like that. So in archaeology they do that. They map that whole terrain of say a ancient temple well or city structure, just by scanning the laser and taking this reflected thing back, and you get that. So you, at that point, you might choose a laser which is in the near infrared, which can say bypass these trees here. Okay, it will bypass these trees here, and it will go down to the level. But then suppose you want to, you are not interested in bypassing the trees. You want to have a general knowledge of what is around, including the jungle, the trees, the river bed, and such. Okay, then you can choose a visible light wavelengths which are from in the Vigbio region. Okay, and you do your work there. Okay. So next I will just tell you the difference between radar and LIDAR, how they are different. They are very similar in many cases, and each of them have their positive points and their negative points. So I think it's important to discuss that, because the radar was the original detection and ranging system, and LIDAR came later on.